All right, so what we're looking at here is a company who's looking to purchase two insurance plans with two different types of coverage each. So I'd like you to take a moment, pause the video just so you can take a read at the problem. All right, so hopefully by now we have a good sense of what's happening here. So what we're looking to do is minimize the premium, and that we know from right here. So the premium comes from $50 per unit of policy A and $40 per unit of policy B. So this is telling me that, and I'm just going to call it C for cost. So we're going to say C is equal to 50A plus 40B. Normally we use X and Y, but let's give our variables some meaning. So what we're told is that we want to have at least $300,000 in fire theft insurance between the two policies and at least $3 million in liability insurance between the plans. So here is how our linear programming problem is going to get formulated. So we want to minimize C equals 50A plus 40B subject to, remember that's just standard phrasing for these are the constraints that are coming. So we want at least $300,000 in fire theft insurance. So looking at this, fire and theft is $10,000 per unit for policy A and $15,000 per unit of policy B. So that means that this is 10,000 A plus 15,000 B, and we want that to be greater than or equal to 300,000. So I'm actually going to write that down here. 10,000 A plus 15,000 B greater than or equal to 300,000. Okay, so looking at liability now. Let's say liability gives us 180,000 from policy A, 120,000 from policy B. So that means the total cost or the total coverage for liability is going to be 180,000 for every unit of A that I buy, 120,000 for every unit of B that we buy, and we need that to be greater than or equal to 3 million. Okay, and just by de facto, we want A to be greater than or equal to 0, and we want B to be greater than or equal to 0. So what we need to do first is look for or try to figure out what the feasible region is, and we can take some shortcuts here. We know that everything's greater than or equal to, so we know that everything's going to be shaded above. So looking at that, I'm just going to go kind of whip through this pretty fast here. Looking at the first constraint, if A is equal to 0, so I'm going to graph A on the x-axis and B on the y-axis. If A is 0, that means 15,000 B is equal to 300,000, which means B is 20. So I have a point here, 0, 20. And if B is equal to 0, that means that 10,000 A is equal to 300,000, which means A is 30. So we have that. So there we have that. And this is our line right here. And we know that greater than or equal to means I'm going to be shading above, but I want to wait to shade until we graph the other one. So the other line's a little bit tricky. So if A is equal to 0, we have 120,000, B is equal to 3 million, which means B is going to be 25. So I'm going to graph that one in a burgundy, and that's 0, 25. And then for the other side, if B is equal to 0, I have 180,000 A is equal to 3 million, which means A is equal to 3 million over 180,000. I can cross out 4 zeros. I have 300 over 18, divide everything by 6. I have 50 over 3, which is 16 2/3. So we're talking right around here. So we know that our feasible region has a point of intersection right here. And we also know, I'm going to graph it in green because we're talking money, so it seems appropriate. We know that our feasible region is everything above all of those lines and in the first quadrant as well. So the other thing we have to do is figure out what that point of intersection is. Now, you can go to Desmos and whatnot. I'm just going to do it by hand really quick. We know it's a solution to the system of equations formed by these two if we were in equation form. I'm going to go ahead and multiply the first equation through by negative 18, because that'll give me negative 180,000a, so that's going to cancel out with the other one. 18 times 25, that would be 270, so that's 270,000b, and equals, if I multiply that by negative 18, I get negative 54 followed by 5 zeros, so negative 5,400,000, and then I have 180,000a plus 120,000b equals 3 mil. The page has gone wild here. And then if I add those together, I get negative 150,000b equals negative 2,400,000. And that will say b is equal to 16. Okay, great. So if b is equal to 16, I plug that back into one of the other equations. I'll just, spoil the secret right here. That's going to give me a is equal to 6. So I encourage you to try that on your own if you want to pause the video, or just go to Desmos and find the point of intersection. So now here's what we have. We have our quarter points, and we have our value of c is equal to, what was our objective function? 50a plus 40b. So we have 0, 25, we have 6, 16, and we have 30, 0. So 0, 25 means a is 0, gone. 40 times 25 is 1,000. So that's the premium cost there. 6, 16, 50 times 6 is 300. 40 times 16 is 640, and that's 940. So it's smaller just by a smidge. And then for 30, 0, 50 times 30 is 1,500. So we have a clear winner here. If we buy 6 units of policy A and 16 units of policy B, all the constraints are met and we've minimized the cost. But now in number 2, now we're saying, and I'm actually just going to copy down the table here because I'm going to explain that in a second here. We're saying, what if the $50 policy was actually 25? Well, that doesn't change the feasible region because we didn't change any of the constraints. All we're changing is the 25 in the cost function. So we just do this problem one more time, but keeping in mind that it's a 25 instead of a 50. So let's see if that changes the nature of our solution here. So if that's 25, we have 25 times 6 plus 40 times 16. That's 150 plus 640, which is 790. So still smaller. But then we have 750 from the quarter point 30, 0. So that changes our answer drastically. This is saying don't even bother with insurance policy B. Get 30 units of A and you're covered and you've spent the least amount that you can. So there is an example of a minimization problem, and just kind of looking at if we change a couple different things, how does that change our solution? So hope that helps. Thanks for watching.